Thank you very much, Jaime. It was perfectly pronounced, of course, the name of my university, and start to share. And I would like to start sharing this. That is one of my favorite picture that I took by myself in Rio some years ago. And this is you all know that this is the typical way of eating cocoa there. So I hope to come back soon to be able to do it again. But then, and I thank you really very much for the invitation, Jaime and Lucas, because it's a great pleasure and honor to talk here for me. Okay, so let me start as usual. Okay. I start my talk. As Jaime told, I will talk about the topology of constant mean curvature surfaces with convex boundary. So we will try to ask and answer to the following question, which is the geometry and also the topology of, the topology and also the geometry of a compact constant mean curvature surface M bounded by a convex Jordan curve gamma. Okay, it's a very simple question, simple to say, not easy to answer. I'm sorry, I cannot. I always have a problem. Okay, sorry. Now I think I am able to do it. Okay, so the question can be very simply answered in the case where the mean curvature is 0, in the case of a minimal surface. You take a curve in the plane, Jordan, and then you know that the minimal solution is the plane itself. Okay, so this is very simple. But once you have that the mean curvature is different from 0, then you have at least 2 approaches in order to answer to such a question. The first one is assume that your curve, your boundary curve, has some symmetries. And then you can look at the fact that if they can be innervated by the surface. And then you would determine the shape, of course, because if you have some symmetries, the surface has the symmetry as well. So you can start working. And this is the typical case of the 2 spherical caps. A circle, and then you know that you have at least the 2 spherical caps for as surfaces with constant mean curvature and that boundary. Then, if gamma has no symmetries, you can try to determine the topology and the shape of N in some different way. Okay, so the first way is to see if you can recover symmetries, and the other way is to work in a different way if you have no symmetries. Okay, let's talk a little bit about the case with symmetries in R3. That will be not really the subject of this talk, but it's very interesting to talk about that. There is a very nice theorem due to Brito, Mix, Sarp, and Rosenberg that is the more general result in this setting, and goes as follows. You take a convex curve in a plane, and you take a surface with constant mean curvature with boundary this curve. And you want that this surface is transverse to the plane that contains the boundary curve along the curve. Then you can prove, they prove, that M has all the symmetries of the boundary curve. In particular, of course, if C is a circle, then M is a spherical cap. But we have this assumption, transversality, that is an assumption so the result is not as general as we would like. And the proof here has 2 main ingredients. The first one is a balancing formula to prove that M is contained in one of the 12 spaces determined by P. Once you have that, the M, and here, of course, you use transversality. Once you have that the surface is in one of the two half spaces, then you use Alexander reflection method and you get the result. The surface inherits all the symmetries of the boundary. Now, of course, there is a conjecture by Brito, Mix, Sarp, and Rosenberg, and this conjecture is the following. If you take a compact constant mean curvature surface bounded by a circle, then it is a spherical cat if one of the following conditions holds. The first is M is embedded, and the second is M as genus 0. Now, there is no answer to this conjecture after how many? 30 years, okay? The picture is exactly what we would like, one would like to prove, but it's very hard. The two conditions are probably sharp because of Wente Torai. Okay, so I will not enter in details about that. There are some partial results, of course, towards this conjecture, but in fact they all assume something. For example, you can prove that it's fine if the volume enclosed by M and the boundary, the plane that contains the boundary is bounded, or the length of the boundary curve has some bounds, and so on. So there are partial results like that. And then there is also plenty of results in other ambient spaces. Very interesting results by many authors. I will not talk about them. Okay, so this is the case with symmetries. Now, before going to the case with no symmetries, I want just to tell a couple of minutes something about Alexander reflection method. Probably in this audience, everyone knows about Alexander reflection method, but one never knows, so better to say something. The point is the following, is a method that helps to prove that if you have a surface in the space, in this case is R3, but it can be in many other ambient manifold. So with constant mean curvature, and you take a family of parallel plane, that then one of these parallel plane is a plane of symmetry of the surface. So why that? This is not very hard to prove. The surface must be compact. So you take a compact surface, then you will find one of these planes, say P0, far away from the surface, that don't touch the surface and don't touch, of course, the domain included by the surface. Then you approach this surface and you arrive to a first contact point, this plane PT, and then you go a little bit farther. When you go a little bit farther, this right-hand side of the surface is a graph over a part of the plane PT, and then you start to do reflection, so to obtain this orange surface. Okay, at the beginning, everything is very small, so the orange surface is inside this domain bounded by M. And then you go farther, and you continue until you have the first contact point between the orange surface and the blue surface here, the left-hand side of M, in fact. At this point, by the maximum principle, because both have constant mean curvature H, the mean curvature vector points on the same side. So by the maximum principle, this orange surface and this left-hand side surface must coincide. So this means that P tau is a plane of symmetry of M. I'm simplifying a little bit, but it's true. Okay. So this is a Alexander reflection method that of course, if you see, this guarantees that the surface has some symmetries. This can be extended, the use of Alexander reflection method can be extended in many ways, even for surfaces with boundary. So it's a very powerful tool. Okay, so now let's go to the case with the possibly no symmetries. We will tell first what is known in R3 about this case and some generalizations. Then we will talk about what we do in the space Hn cross R for n larger or equal than 2, and this is a joint work with Giuseppe Pipoli, and is in progress. And then we just something that you all know in this audience, I suppose, I'm sure, but just to justify why H and cross R, in fact, H2 cross R, one knows it's one of the first on geometries, and in last 20 years, there has been a lot of work for CMC surfaces in this space, and also in higher dimension. And I will talk a little bit more about that later. This is just a summary of what I will do. And then some plans about the future, if I have time. Okay, so we start by what is known in R3. Just one more thing. For all those cases, there is a strategy in common, but each case needs some different tools. So it's quite interesting, the mathematics coming out of that. So CMC surfaces in R3 plus, in fact, it's in the upper half space. It's a very, very nice theorem by Ross and Rosenberg, 96, Journal of Differential Geometry, that says the following. You take a strictly convex curve in the plane, then there exists a number depending on this curve, on the curvature, in fact, of this curve, such that whenever m is embedded in R3 plus, so the upper half space, and there's constant mean curvature between 0 and h of gamma and boundary gamma, then m is topologically a disk. So no topology at all for m. Moreover, you determine also the shape of m, that is exactly as in the picture. I mean, is a graph here, what I called n. So in the cylinder above the boundary is a graph. And also what is outside is a graph with respect to the horizontal line going out of the cylinder over the domain omega. Okay, so this is a beautiful theorem. And the tools for proving this theorem, first, you need the height estimate. Everyone, I don't know, but it's well known that a CMC surface with boundary in a plane can be at most of 8(2) over h with respect to the plane. Okay, so height estimates are very important here for this proof. Then Alexander reflection method, I talked to you before about that, and a blow up theorem. Okay, of course, I'm not going into details of the proof, but I want to talk a little bit about that because the blow up theorem is a very interesting theorem. And let me state it and then explain you why is important for this theorem, this blow up theorem. So the blow up theorem goes as, in fact, a way of telling this blow up theorem is that if you no, maybe not, maybe I will tell it later, sorry. So let me state the blow up theorem. You take a sequence of CMC surfaces, all with curvature h equal to 1, and with boundary in a small disk whose radius is going to 0 in the plane, and a small disk with radius going to 0. Then there exists a subsequence that converge either to the origin or to the sphere or radius 1 tangent to the plane at the origin. Okay, so this picture, in fact. There is also something about the convergence, but this is not very important, the type of convergence, not for us in this moment. But the point is this one. So the red stuff, the red stuff here, the red surface is the sphere, and so there is a subsequence converging to that. Okay, so the proof of the blow-up theorem is not very difficult to imagine, because by height estimate, as I told, all the men are contained in a compact subset of R3. And this is because all of them have the same mean curvature. Then one can prove that far away from the boundary, this is by Alexander, had a lot of some work, far away from the boundary, all the elements are graphed in some system of coordinates locally, okay? So by that, you have uniform area and curvature estimates. This guarantees, by compactness theorem, that there is a subsequence of Mn converging in compact subset of R3, minus this little segment above the origin. Okay, there you have some problem because you approach, the boundary is going to 0. So there you approach into the boundary, you don't know what happens. Then, if the limit is empty, it's not hard to see that the surfaces converge to 0, in fact, not only to the segment, but really to 0. Otherwise, the subsequence converge to a surface different from the empty set. And Alexandrov reflection method with vertical hyperplanes can be performed till the boundary, but the boundary is going to 0, Rn is going to 0, so it can be performed till the origin, in fact, and you can prove that every vertical plane passing through the origin is a plane of symmetry. So M is rotational. And as the height is at most 2, it is the sphere. So everything converges to the sphere. Everything. There is a subsequence converging to the sphere. Now, why this theorem helps for Ross-Rosenberg theorem? This is because you can consider the blow up theorem and rescale it by doing dilation of ratio 1/Rn, the radius that shrink the boundary. Then Mn tilde, that is this rescaled sequence, has mean curvature Rn times h, of course, by rescaling, and the boundary is contained in the disk of radius 1. Okay. So by the blow-up theorem, you have that your Mn tilde is close to a sphere of curvature Rn times h. That means a very flat sphere, because when Rn is going to 0, this curvature is going to 0. Okay, so this is important. The upper part of Mn tilde is very, very, very flat. So if you cut a sphere towards the next to the top, to the North Pole of a fixed height, and you make the curvature smaller and smaller and smaller, the sphere is doing this picture. So the surface M that is close to that is very flat. Okay. Now, and this is very important for, you will see that I will not say why really it helps for Ross-Rosenberg theorem, because you will see it later in my proof. Not really that, but you will see, you will remember about that. Okay. Okay. Now, a couple of generalization of Ross-Rosenberg result. The first was by Semler, that extended the same result in H3 with boundary in a horosphere, analogous result. And then myself and Semler, we extended the theorem to the case of hypersurfaces in Rn+1, which have HR, the higher order curvature, one of them positive constant. Okay, so even in that case, there is no topology for the surface with boundary in the plane, under condition, of course, on the curvature, on the mean curvature, or on the HM curvature. Okay, so now the generalization in HM cross R that we did with Giuseppe Pipoli. As I told you before, HM cross R is a special case, but it's a toy case of a general Riemannian manifold. It's interesting because it is a product space, so it has non-constant sectional curvature, but has many symmetries, because HN has many symmetries and R, okay, is R. Okay, so it's a you can work in HN cross R. And let's see which parts of the proof do not survive here. The first part that does not survive is the blow up, because dilation in HN are not dilation. You can say there is no dilation in HM. So you cannot, the blow up theorem doesn't make sense. And then there is another part that is important that does not survive. I told you before that when H is going to 0, then the sphere, the real sphere, is flatter and flatter near to the top. Okay, here, when H approaches the critical value, that is not 0, here is n minus 1 over n. In the case so of n equal 2 is 1 over 2. Then the compact rotational surfaces, hypersurfaces here, analogous to the sphere in R3, are not very flat. Look at the picture. This is the situation. This is the picture of the profile curve, of course. This is, here I consider the H2 in the disk model, and then I have the component R here. And then the compact CMC hypersurfaces, I will say surface very, very often, but are converge to this red surface, in fact, that is a complete graph on H2. So, and you see here, they are not flat next to the origin. Okay, the red surface is not very flat next to the origin. Okay, so this is a problem. You cannot really do the same thing that you do in the case of R3. So let me state the generalization of the Ross-Rosenberg result. It's almost the same theorem. I mean, there is just some assumption that is very natural due to the fact that this boundary, this surface is not going to be flat. So let gamma, I state it in any dimension, but then I will do a sketch of the proof, and this will be only in 2 dimensions. I mean, in H2 cross R, but it's the same. So let gamma be an n minus 1 dimensional manifold in the slice t equals 0, and then an hypersurface embedded in the upper half plane, even here, with boundary gamma and constant mean curvature h larger than n minus 1 over n. Assume that gamma is almost rounded small. I will say in a moment what does it mean precisely, but it is really almost rounded small. I mean, you can imagine geometrically is very easy to imagine. Then n is topologically a disk. Moreover, you have that the shape is the same as before. Graph and graph in the horizontal direction. Graph in the cylinder, a graph in the horizontal direction outside the cylinder. Okay, before telling you about this almost rounded small assumption, I want to talk just one minute about this assumption, h larger than n minus 1 over n. That is the critical value of the curvature here. Critical value, I just tell why this is the critical value. One of the reasons why it is the critical value. There is no compact, how to say it? There is no compact rotational surface of constant mean curvature h smaller or equal than n minus 1 over n. It's like in H3. In H3, there is no compact CMC surface of h compact rotational, let's say rotational, of curvature less than 1. And here, the value is n minus 1 over n. Okay, so this changed completely. It's like in R3, there is no compact minimal surface. It's the same. But in this case, it's not really a restriction for this theorem, because in fact, some years ago, myself, Sarp, Santos, and Tubiana, and in the case n equal 2, and Berard and Sarp, in the case of a general n, proved that if you have an n minus 1 dimensional manifold in the slice, oroconvex with principal curvature larger or equal to 1, and if M is an embedded hypersurface with boundary gamma, and constant in curvature less to or equal than n minus 1 over n, then M is a graph. So we already know that it is topologically a disk. Okay, so the methods are different for this case. The methods are different for this case. So the interesting case the open case. Now this case is also interesting, but the open case was just H larger than n minus 1 over n. The assumption on the boundary. I will tell it in the case n equal 2, but it's exactly the same. So we take a curve. We consider the maximum and the minimum of the curvature, both larger than 1, because we want to be oroconvex. And we call Rx and R int the radius of the circle with that hyperbolic curvature. Okay. Then, of course, it's clear that it's straightforward to see this picture that the circle with the radius Rx is outside the curve gamma if you put it tangent to any point of it, and the blue one, the circle with the radius R int, is inside. Okay. Then gamma is almost round if K max and K min are not very different one from the other, obviously, and is small if the exterior radius is small. Okay, so these are the assumptions. And they are because, in some sense, you have to be compatible with that surface that I showed you before. Okay, so I will do something very dangerous because I'm going to change my share file. Okay, because I want to show you something else. So I hope it works. And just to do this now, wait a minute. Let me just open that. Okay, so that I can write here, but I want to take out this. I don't know how to do that. I don't know. Okay, anyway, I hope this does not disturb too much, this small stuff. Okay, so I want to show you, I have some minute more, I think. Yes, I have 10 minutes more, I think. So I want to show you how to prove this theorem, a sketch of the proof. I hope you can see me, my screen, I mean.
Yes, it's okay.
Thank you very much. So the proof, in fact, I will do just one case of the proof, the most interesting one. That is, you know, you have this surface M, as I told you before, as in the assumption, with boundary gamma, and I assume that this let me take the green, that this H max of M here is bounded below. Okay, in the case it's not bounded below, in fact the proof is easier because it's a small surface, so you can manage in a way that is easier, in fact. Okay, I will not present that. I will talk about large surfaces. Okay, so H max is bounded below. Independently on M, it means that it depends only on H, on the curvature. What we do, the strategy goes as follows. One can find a disk D in omega, that is the domain bounded by gamma, such that in the cylinder over the disk here, M is a graph. In this small disk, a small disk with radius R min. One can prove that. Okay, then second thing that one can prove is that if you choose an HD small enough, then you can find at this 8 H max minus H of D a disk of radius R contained, as in the picture, in the component W that is bounded by M and the domain omega. okay? This, in the Euclidean case, was done by using the fact that the surface next to the upper part was very close to the sphere. Okay, so it was very flat, so you could find a disk of large radius r inside. Here we have to manage in a different way. Okay, but with radius r, this large, in fact, here is not really large. In R3 and H3, this large means that r was going to infinity by becoming flatter and flatter, the h, when h was going to 0. But here is different, okay? As we told before, no? We cannot say that it is going to be flat. But then we get an r. Now assume that you have 1 and 2. So the small cylinder, and where it is a graph, and this large disk of radius r at this level, h max minus hd. Then you start to do Alexander reflection with the horizontal planes. You start, you reflect, you reflect, you reflect. And what you can prove, if you are careful, is that in this part of the domain W, this is the domain W. So in this cylinder, over the disk of radius r, there is no surface. Okay, because if there was some surface, you would have that by the maximum principle, you would have that the upper part would coincide with the lower part because it would be a plane of symmetry, and this is impossible because the lower part has a boundary. But in fact, you cannot really approach the boundary. You have to stop at a certain hd here, at a certain height here. But then you have no surface here inside. So this is a good news because all the problem that you can have are, let me change the color, are here around, I wanted to change the color, I didn't change, are in this small box here. Okay? Okay, but now let me tell you about a very special rotational surface that exists in this space and does not exist in the, does not exist, of course, but it's here it has a very special features. There is in H2 cross R and also in H1 cross R a rotational surface where the profile curves is given by this green curve. And the important thing is that when this parameter is a one parameter family, when this parameter go to -1, then this loop, the green loop here, becomes smaller and smaller. Everything goes to 0. Okay, so in fact the surfaces are converge to these two surfaces like that. This is quite different from the, for example, the catenoidal case, the catenoids in R3, because the catenoids, of course, is not. If you consider, for example, this red part here, okay, and then you do the same for the catenoid. So the catenoids, you know that the catenoids in R3, when you shrink, in fact, this is going to the double cover of the plane. So it's quite different because it's going to be very, very flat, in spite of the fact that the height can be, it occupies, it's not contained in half space. Okay, here is quite different because you can control this height, and the relation between the two heights are very, very interesting for these for our purposes. Anyway, remember this small surface of this red surface and rotate it, and you can succeed in put it here exactly where I put in the picture. Okay, in fact, you cannot put directly there. You have to manage, because you want to put there the surface in a way that it doesn't meet the orange surface, your original surface. So in fact, you have to put, okay, sorry. You have to put first the surface here where there is no surface, then you go down, you have to work a little bit, but then you can put the surface here. And what you do is just to take this red surface around here in the in the domain omega. And as it is very small, so you can touch every point of the boundary, and you see, and you cannot touch the surface, because if you touch the surface, then the red surface and the orange surface should coincide, and this is impossible. So you can, if you are able to put around, to take around this red surface everywhere, you will push outside the cylinder over omega all your surfaces. So there is no surface here, there is no surface here, no surface here. And outside is fine, okay? So the condition to be able to do that is that this upper boundary does not touch the surface when you go around. And the condition is given by this R, the R that determines your cylinder, larger than Rx plus R max minus R min. Okay, so in R3, the condition was very easy because this was going to infinity. Here, we have to really compute and evaluate everything, okay? But it works, and it works because of this very, very nice construction that is the limaçon construction. And with this, we are able to evaluate all the quantities and prove that it is possible to make the good choice. The limaçon construction, it can be done in the hyperbolic space. It's an Euclidean, sometimes it's called the pedal curve when, but this is more general in fact, but it's something like you take a circle, you take a point, and then you take a tangent to the circle, and you construct the curve that is you do the symmetry of this point with respect to the tangent to the circle, and you take the symmetric point. The set of all symmetric points when you move along the circle is the limaçon, or the pedal curve of the circle. So what you can prove is that you can do this construction also in the hyperbolic space, and you have that the smaller loop contains a circle that you can, of which you can control the radius. And this helps for controlling everything. You can imagine, I'm doing symmetries for the limaçon construction, and Alexandrov is symmetries. So you can see the relation between these two things. Okay, I think I am done. Just, okay, generalization are very, you can imagine them. Different curvature functions, and also mean curvature, non-constant, but pinched. Okay, we would like, these are something we are working on. Okay, so thank you very much. And I finish with this wonderful picture that I took. So I'm very proud of that.